department is one of the best schools in the world regarding education and research. So, yeah. Great, so the outline of my research here, we have a definition of what structural health monitoring is, what is the motivation and background for structural health monitoring, the objective of structural health monitoring, then the flow process of what it is. So these are quite simple terms, excuse me if it's not, high level for everyone, because I just wanted to have something inclusive that everyone can have a bit of understanding. Then I'll talk about the lifetime of structural performance and different techniques for structural health monitoring, and at the end, self-sensing concept that my colleague is going to also introduce more detailed examples. Yeah. Well, as I'm now in civil engineering department, this example that I've given is about civil structures. However, you can, widen the example to other applications, and we have an aging infrastructure, expensive buildings, roads, bridges, wind tunnels, wind turbines, tunnels, and many other structures that are aging. And we need to understand how they are behaving in long term. We need to make sure that we understand their degradation process in order to evaluate their performance. And so we have challenges about, that they are being neglected and deteriorated, and there's lack of funding to replace or repair. So it's a global challenge and something that needs to be addressed. And there's a huge market that is predicted in this direction. So about the material health monitoring or structural health monitoring, there are variation of materials, and there's different techniques that are being used for manufacturing. There are lots of defects during construction and production. Then there are design uncertainties. Not always those that you are designing are going to be as perfect as you think. Then there's environmental conditions such as temperature or humidity, corrosion level, and other parameters affecting the structures, and the damage such as corrosion, cracks, segregation, settlement, and many others can happen during the lifetime of the structure. So structures deemed unsafe and unserviceable, and they need to be replaced, and the reduction in strength and serviceability that is caused due to the degradation, and the repair cost is sometimes comparable or better than the replacement cost. So these are some of the motivations why we go to structural health monitoring. So there's a need for it. Yeah, we go. So structural health monitoring is, so I tried to show the structural health monitoring system analogous to a human body, because in our body we have nerves, and those nerves are acting like sensors. So if you have a pain in your body, the nerves would send a signal to your brain that my body has a problem. I'm aching. Some part of my body is not working as it should be. So your brain then makes some decision based on the signal it generates. And it's quite similar to the same concept that we have some sensors in different structures, then we get the data from those and we send them to a controller, and then that being processed and the decisions are made based on the data that we gathered. So integration of sensors is sometimes actuation as well, and we understand what is the condition of the structures that we are monitoring or we are reporting. Well, what if we don't do, or basically why do we move towards structural health monitoring? Current designs in engineering are overly designed, you know. So when we say overly designed, it means that we put a high safety factor in the structures. When we are, for example, designing a bridge, we put too much safety factor. And what that does, that increases the cost. That increases the weight, that increases the waste material, that increases the use of raw material, it produces more CO2 emission. So that's a challenge. And they also design for damage tolerant behavior. They design the structures to make sure that even there is a problem, it's not going to fail because they cannot tolerate the cost, because that can cause harm to the humans, or there can be catastrophic failure causing issues, like imagine an aircraft flying and it crashed, then people are going to die, or similar examples. So as a result, they put a lot of safety factor, and they also design for damage tolerance, and they try to make sure that it's not going to fail. Another alternative option that they do is periodic inspection. So they send someone, for example, to a bridge to look up what's going on in the structure. They visually see and understand what's happening, and they use that, or they do non-destructive evaluations such as visual inspection, ultrasonics, and eddy current to understand periodically what's happening. But the challenge on using those is that you are doing periodic inspection, and something may happen in between, and also it's not an effective way of doing it. So this is the conventional structures. We say, okay, this is the other approach is that actually we say we design smart structures. What is a smart structure? The structure that can sense itself and respond or adapt to changes in the environment. So it means that you understand what's going on in the structure and you act accordingly. So they have many sensors that they get the data, and then they can enhance the performance and also increase the life cycle time, or reduce the cost that you are spending on overall the use of the structure. So here is the overlap for this smart structures. You need to have sensors, structures, and sort of that they are designed nicely to perform in a way that we have a good understanding of the structure in situ or online. Well, just to make it even simpler, you go to the doctor from time to time, or you check your health status to make sure that everything is going nicely. So it's similar to this, that we have our sensors and structural health monitoring that we are using to get the data and then make decisions for the maintenance plans, such as repair or replacement, and make sure that everything is in the order. So the objectives are health monitoring, operational evaluation, the data extraction and analysis, and also the decision-making process at the end, which is done by algorithms such as statistical models. So the support for decision-making or structural safety, strength, integrity, and performance is done using this process, and also the move we made based on performance and smart structures. So you see that structural health monitoring is a combination of different knowledge that we have of development. We have sensors, NDE techniques, modeling, reliability, service strengths, and then the condition monitoring. So all these combined gives us what we want, and we have reduced maintenance costs, extended service life, and also improved safety in our structures. And here is a simple example of a structural health monitoring system, how it works. So we have our structure. This is, in this case, it's, for example, a blade, a metallic blade, like that is used, for example, for engines blade. So you have the sensors. These sensors are gathering the information and they are passing it to a data processing system using a data acquisition system. So you have the data processing system, then you have a control unit where you get the data, you analyze the data using the simulation models or like predictive algorithms, and also predict what's going on with the lifetime of the structure, what are the abnormalities and all those. And once you evaluate them, you do prognosis, and based on that, you do maintenance. And for example, self-healing, which is another concept that that is, for example, you know what's going on, and you then have some agents that they are being activated once you have understood what type of repair you need. So that's also another step after self-sensing, which you actually design some agents. And here, what are the parameters, for example, you have? Different type of sensors, such as strain gauges, temperature sensors, humidity sensors, and many others, which I'm going to briefly talk about them. And you have the data that is fusion, like or gathered together, the data management system, the analysis, and the reporting and alarming. So at the end that you make the decisions. Yeah. Why it's becoming popular? I discussed about this, but just to summarize again, it's important to know why we are moving towards abstraction. So because there are also some materials and some innovative designs that we don't know how they behave. Traditionally, we had metallic structures, for example. We had a good understanding of their behavior because we did lots of experiments with them. We designed them, we tested them in experiment, we understood them. However, there are new materials and new designs that if we want to do the same with them, we have to spend a lot of resources and costs to characterize them. So like different type of composite materials or type of materials that we are developing, and they are being developed every day. And simply it's difficult to do that because you cannot afford to do. And we also need to have a better management of existing structure. So that's why we use structural health monitoring techniques to have an understanding of what's going on online and in situ, rather than rather than doing experiments and characterizing them. They're using that knowledge to design and to have a conservative. So also there are new developments in sensors. The sensors are becoming cheaper, becoming easier to operate, low power, and now it's Internet of Things and connection of the sensors have become easier. So the data acquisition systems are developing. We have wireless and internet communication systems that are becoming easier and easier every day. And then the data transfer is also a research area that has been developed quite a lot. And of course, this data processing, such as artificial intelligent algorithms that are being developed. So we are in a good position to move toward this structural health monitoring because we have all the resources and all the things that we need, that everything is taken. And here what happens when we use structural health monitoring techniques. You see, we have the time life cycle of this structure, and we have the performance of this structure. So this is the black line here is the line that you have below the structural health monitoring system. And the ideal that you have designed is this dashed blue line. So you have designed the structure to behave like this, but in reality it behaves like a platform. And the reason is the uncertainties that you have during operation. Not all the structures behave the way you design, not the loading conditions are different. And you can't predict all the uncertainties. Then what happens? You have to shorten your life cycle. You have to replace quicker. And that's the optimistic situation. But there are situations that we have designed for this and it fails at this. And imagine an aircraft that is designed to fly a specific number of cycles, but fails in the middle of the air. Well, we cannot do that. It's costly, it's dangerous. As a result, we always tend to replace them earlier. So we don't want to risk our life, or we don't want to have risky, catastrophic failures. So what happens using the structural health monitoring systems, we occasionally or continuously monitor the structure. If there's a problem, we improve it, and then it goes, then we improve it, then it goes, and then we have the extended life that is matching the design life. Then you have a better performance in a longer run. So you're extending the lifetime of the structure. So just to give you an example, for example, these wind turbine blades are good examples that now everyone, like most countries, moving toward production of green energy. These wind turbines, for example, have to last 25 to 30 years. But what happens, as they are not certain about their performance, they usually throw them away much earlier. And that poses a lot of problems because they have to, they cannot recycle most of the parts. They have to put them in the landfill. It means that there's pollution. And if you can extend them for 5 years more, for example, you save a lot of cost. You're reducing the pollution because you're reducing also the raw material usage, and you're reducing the rubbish that you're putting in the landfill. So that's just one example. And here how it works, you have an optimal solution for structural health monitoring as well. Of course, you need to design the system to work just fine, but you don't want to spend too much time because you can gather all the information and all the data, but why should you? You should just take the data that is important for your decision-making process, not everything. So that's also something to consider, that there is an optimal solution for structural health monitoring, like anything else. When you design something, you try to have an optimal solution. All right, there are different stages for structural health monitoring. We have level 1, which is the data presence, which just detects the presence of the damage. It means that our sensors and our structural health monitoring system is just designed to detect that there is a damage. It just gives you the warning. It doesn't give you any more information. It just says that, okay, there is an abnormality in your system that you need to work on. The second level is that you detect the damage, and you can also know where the location of the damage. So you have the damage, you know where the location is. The third stage is you detect the damage, you know the location, and you know the severity of the damage. So, and you have data about this location, and existence, severity, and also the consequences of the damage. So what is causing, what this damage is doing? Is it reducing the lifetime? Is it important or not? So it depends on the application, depends on the structure, depends on your situation. You may choose to have different stages of structural health monitoring. You may not need to have level 4 in your structural health monitoring system for one application, or in another application, you may need to have level 4. In some applications, it's just good enough to say that there's a damage, and then you just throw it out like away, or you replace it, or you do something about it. That's what you do. But in other cases, you may need to know, okay, what is the effect? How I can do better maintenance, how I can do a good repair. Then you need to know, what type of level you need to choose based on your requirements. And we see that when we increase the level from 1 to 4, what happens? We are actually increasing the sophistication. Of course, it becomes more expensive. It becomes more complicated when we increase the structural health monitoring levels, because we want to know more, so we need to spend more. We need to understand more. We need to get more data. We need to better analyze them. And then it becomes more sophisticated and more expensive. So there are then, a decision to be made as engineers, okay, we actually need this much information, and that's enough for us. So that's something to be decided. And of course, you see that the higher we go, the complicated and the more costs we have to spend. Well, again, to emphasize, for example, level 1, we have the online load monitoring, which detects any loading which are imposed to the structure. So it's the most basic way of doing it. It only checks whether the structures work as it should be or not. And it doesn't say anything about, what are the problems. Okay, we have level 2, there's a damage. We identify the damage location, and also, whether the damage exists, where is it located. It can be used as an initiative for have better maintenance, and it gives you some knowledge, but also lacks some other information in this. And level 3, as I discussed before again, you have more information, but also you need to, better understand what it may cause to the structure which we are missing in this. If we go to the level 4, here we have more understanding of what that damage poses to the structure. So we make better plans, okay? And of course, before all those levels, we have level 0. What is that level 0? Is quality check. So all the engineers, they have to make quality checks. For example, when you are installing a system, you should make sure that it does have the minimum defects and damage in the installation process during the manufacturing phase. We should try to minimize all the problems. As a result, so this is, even before that, you have to have a good quality check. And now, even this process is becoming automated. It's not just the engineers do this. Also, for example, there are robots that they are checking the quality of the product during manufacturing, so that they can have better understanding of what may happen because of the structure and the type of damages that sometimes are not easy to avoid during manufacturing or assembly. So then you have an understanding. And then, if all the structures are designed properly, you'll be still in structural health monitoring. So, what is the answer to this? Is it a yes or no? Yes. Why is that?
Uncertain.
Because of
uncertainties.
Because I think I explained enough. So hopefully everyone have grasped what structural health monitoring, why we still use it. Eventually we have a perfect design. It doesn't mean we don't need it. We need it because we want to have reduced safety factor, cheaper designs, use of less material, longer service life. So we still need it because of uncertainties. Yeah. So the advantages are Yeah. It's not coming? You can guess. What are the advantages? Okay, it's already there. So increased understanding, early damage detection, assurance of structural strength and serviceability, decreased downtime, development of rational maintenance, increased effectiveness in allocation of resources, enabling and encouraging the use of new and innovative materials, better safety assurance, cost saving of inspection. You know, they are still using inspection now, but they are not using it cost effective. So this helps that way as well. Yeah. Of course, there are disadvantages. What are those? You will see soon. All right. So we have high installation costs, vulnerable to ambient noise corruption. You know, you get challenges because it's not easy to get the signals and the data you want. It becomes difficult. It's vulnerable to earthquake condition, you know, or other uncertainties. You know, it depends on the application and situation. So accessibility, it's not always easy to put the sensors. For example, if you have a large structure, you know, it's not easy to detect the data from that. If you want to use cables, sometimes you have to use too many cables, that becomes difficult to do that. Wireless communication systems have a range that they can transfer the data. So yeah, issues with that. And also, of course, long-term reliability of the sensors are challenging. Size and complexity, as I mentioned, you know, how many sensors you need to install, how you're going to effectively manage the data. They are all the challenges that you face. And that's why we do research on structural health monitoring to avoid and overcome these challenges. Yeah. Well, damage detection mechanism, it can be local and direct measurement. So you have a local problem like cracks, corrosion, delamination, and other type of defects that you may get in your structures. Then you have the use of acoustic emission to listen to the signals and to the structures. And then you have direct stress measurements and ultrasonic NDs, like you have pressure sensors, temperature sensors, moisture sensors, corrosion sensors that you can use to detect. And the local and indirect measurement, you understand the behavior of the overall structure, not the local, and you use dynamic behavior monitoring, like vibration-based monitoring solutions and others. Or you look at the stress distribution or strain distribution in your structure overall. Well, there are some information that you also need to understand in your measurements, because measurement has, you know, some technicalities that you need to consider. You need to collect the information, and usually under controlled condition. You need to have a controlled situation to know what you are collecting. You know, the measurements tell about that these are the status variables. It has to be selective, it has to be descriptive. It has to, you know, you need to select what you want to monitor. What are the data that you are going to collect? You need to be objective. You know, it has to be independent from the person collecting the data. And ideally, you need to make it reproducible and repeatable. So you're collecting data that are reliable, reproducible, and you can trust them. Right? And here are some issues that you may have. We call it sensitivity. If you're measuring the data, if you're collecting the data, one of the issues is the minimum detectable shift in the environment. Your damage size or your variable, your parameter might be small, you know, and you are not able to detect it with the sensor you have. So you may choose the wrong sensor, wrong monitoring solution, and then you don't get the sensitivity that you have. So you have to check for the minimum sensitivity. You have to check the detection accuracy. meaning that you get signals and also noise. There are noise signals in the environment. You may get the signal from the wind, and you may get the signal from the load. You need to understand which is which. You need to have a high signal to noise ratio. You have a resolution, the smallest change in measurement that is detectable in the sensor. So meaning that if you change a variable, what would be the equivalent change in the sensor data? So that has to be also high enough for you to be able to detect the signal from the noise and also detect what you want. It has to be reproducible. You need to, if you continue doing measurements from using one sensor in a control condition, you should be able to get the same result no matter how many times you do it. Of course, there are variables that in some cases you may not do, but ideally you should be able to reproduce it. And there's a range. What's the range of the application for each sensor and each data? So those are all important parameters. And I've tried to sort of summarize all in here. So you see this is accurate and repeatable. These are all in the same center. You have a accurate and repeatable data. In this one, it's accurate. So it's not accurate, but it's repeatable. You have the sensor that is measuring, that can be repeatable, but it's not measuring the right one. Here, none of them, not accurate. It's accurate, but it's not repeatable. It's quite close and not repeatable, not accurate. So that's why you need to understand these terminologies. Okay. All right, the data acquisition system, the collection of data. For example, strains, the formation, accelerators, temperature, moisture, that is being done. So one of the areas is about selection of the sensor. What type of sensors should we choose and why? So it's different for different type of applications, what we are going to do, what we discussed about the resolution and all the other parameters that we took. So that's important to know what type of sensor we want to sort of select for this. And then we have the sensor installation and placement. We should be able to understand what is the effect of the sensor on the structure. In some cases, if you put the sensor in the wrong place, or if you don't have considerations in this stage, you may actually cause more damage to your structure. So you need to know why, where you're putting, and also what is the effect of that sensor in the long run in the structure. Is it going to have a problem or not? And also many other features. So how are you going to transfer your data to the acquisition system? Is it going to be using wire that you all familiar, and also wireless? So these are also different decisions that you make. Not always wireless is the best option. Sometimes you need to transfer a lot of data. Sometimes wireless systems are not strong enough or accurate enough to transfer all the data. So it's a bit of understanding on the problem and then choosing the right solution based on that. Right? Data sampling and collection. How much data should you collect? Should you just get all the data? No, of course. You have to understand how much data you require in order to make optimal decisions. So that's why you need to understand it. And the issues are how many sensors should you have? What should be the sampling rate? What should be the data sorting for the storage? What is the volume of this data that you need? And also all these, you need to have efficient strategies for data sampling and storage. So, all right, so far I talked about structural health monitoring in general, what are the requirements you have, now I'm going to give you a little bit of introduction on type of sensors. How much time do we have? About, are we halfway through? Yeah? All right. I mean, I'll try to go with the speed I had. I think it's a good speed, and then we can have a conversation after anyway. So, yeah, so I'm now going to talk about, just some of the common methods that are being used in structural health monitoring and NDE, or non-destructive evaluation in general. So, visual, this is the visual sensors. So this is a chart that is showing you what I discussed. Depend on what you want from your health monitoring system, you have to make some decisions. You have to make some choices. You see, here is the deployment time. Deployment time, the higher the deployment time, the better it is, because we want to make it easy to deploy. We want to have a fast deployment process. But not all the techniques are easy to deploy. So ease of deployment and the cost. You see that visual inspection is still one of the best solutions. And the reason, because it's easy to deploy and it has a low cost. So that's why you see still in many structures like bridge monitoring, they still send someone to do visual inspection because that's cheaper. Of course, there are challenges, it depends on the operator, the skill of the person, and the data collection is not as it should be, and many other issues that we can discuss, and that's why now we are moving towards automated visual inspection. But still one of the good solutions. And then we have sensor-based solutions like temperature analysis or vibration-based methods, and non-vibration methods that are like ultrasonic techniques, acoustic emission, thermography, and a few other things. But you see that you have a higher cost for the system, and also they are not as easy as it should be to deploy. But sometimes they are the best solutions. So having a higher cost does not mean that you do not use the technique and you do not need the technique. It just, you need to do a good analysis before choosing one method or another. It's not just, okay, we have a sensor, let's just use it. No, you should have a critical thinking, okay, which one should I choose and why? Why not this one or that one? And that sometimes becomes challenging because you should have a good understanding of different processes and the cost and all the other performances to make a good decision. Right? Yeah, so this is visual inspection that is widely used, one of the most widely used inspection methods that are also being used now in structural health monitoring. So most basic and common, the tools that there are some tools that are developed to make it easier, not only by the naked eye, but also using some tools that are being developed. I've mentioned a few names here. So they use magnifications and borescopes and fibroscopes and a few other things to make it easier for themselves to detect and look at. But the challenge is that not all the structures are easily detectable visually, because sometimes the damage is not happening on the surface or inside. It might be easy for some metallic structures because they are easy to detect from the surface. For some structures like composite materials, which Dr. Suarez is going to present, there are more challenges because we have hidden damage. You don't see it, but the damage exists, and that can cause problem. Then the portable inspection solutions that they are using robots and sweepings or UAVs and a few other methods as well. The crawlers and a few other things. There are lots of research going on in this direction. Okay. And here are some examples. You have a concrete structure, you have a crack, and you want to detect it and make sure that this is not a critical crack, or structure can still do the job that it has been designed to do. Or you need to do something, you need to repair it, replace it, or make a decision So that's why you do measurements on, showing different structures and how they are being inspected, right? Strain gauges. I guess most of you should be familiar, but strain gauge, if you don't know, is the way you measure the strain, and strain is the deflection, displacement, elongation divided by the initial length. It's a simple term that's being used, and it's important to measure the strain level in structures because we want to know what strain level they are so that we can decide whether, that's because if there's damage, the strain level in the structure may go up, may go more than what it has been designed for, and that can cause earlier failure. So that's why, for example, we need to understand what's going on. Okay? And here is an example of a strain gauge, how it's been designed. So it uses like a that's a conductive material that is changing during the voltage or the resistance of this is changing the gauge factor and all those, some equations how they calculate it. I'm not going into the detail, but so basically when we have this on the structure, it changes the resistance, and then from the resistance we can connect it to the strain level in the structure. And here are some examples. This is, for example, Rossett strain gauge, where they use 3 strain gauges at the same time in the same location to have readings from different directions and to be able to find the principal strains, which some of you may have already heard about, because that's the one that is causing. Because the strain might not be critical in this direction or in this direction or this direction, but there might be a plane, an inclined plane, that the strain is maximum, and you need to know that one in order to calculate whether your structure is going to fail and whether you are safe or not. And some equations that they connect the strain measurements from Rossett in different directions into any arbitrary strain, in the direction they wanted. So again, this is more circle calculations that you might have here already, right? So fiber optics. This is another method that is being used mainly for strain monitoring, also other purposes, moisture monitoring and a few others. And how it works, you have this structure that has some coating and elements, but also you have the core with a higher index of refraction than the cladding. And when you transmit a light through it, it changes, some of the waveforms are absorbed and the others are not. And by changing the strain level, the waveform that is being absorbed, this changes. And from that, we can understand what is the strain level. So here how it works. So you have different waveforms, some of them disappear by changing the strain level. That's how simple I can put at this stick. And of course, it depends not on the strain, but also on temperature, pressure, and a few other parameters that you can sense. You have the light, it goes through this fiber optic, we detect it, and from the change in the waveform spectrum, you can say what is the size of the strain, for example, or the temperature. Of course, there are issues how about the intensity, phase, polarization, and things that you need to understand with the measurement. And this is one of the widely used applications. They are now used more than strain gauges because it's easier to have long fibers that are distributed all over, for example, the bridges and all those, to have continuous monitoring that is usually. Well, acoustic emission technique is one of the techniques that I have worked quite a lot. This was my master and PhD thesis actually at the time. And I'm working on other methods as well, but I have worked quite a bit with this, and we had some work with Dr. Schwartz as well on this on monitoring composites. So this is basically you have the source and you use some sensor to detect this signal. It's like, if you have Like a wooden structure, you might have a stick that you have, used your bare hands to fracture. And while you are doing it, you can hear a sound, like a noise that says, okay, it's fractured. And that's generated by the cracks that are being developed during the fracture process. So it's a passive method. You have a crack or a source of mechanical wave, which is sound, and you have a sensor that propagates through the material, and you can hear it. And once you hear it, it's similar to use this detector that monitor your heartbeat, that they put and they listen to the heartbeat and they say, okay, if you are okay or not. It's quite similar concept. But we are listening to the sounds of the cracks. So the crack has to be active in order to generate. So it means that it can only detect the active cracks, not the passive. And there are different types and versions of the sensors that I have tried to show some of them here. They are usually working based on piezoelectric properties. And then you have a strain that is applied to the piezoelectric sensor, and that changes the mechanical strain or mechanical wave into a voltage output. Now we are in our research group, we are developing new type of piezoelectric materials that are more flexible and easier to work with and to reduce the faultiness of the sensors. So that's one of the directions now we are working. And here is the acoustic emission parameter, what you get as a wave, and there are like different parameters you define. And based on this, you evaluate what is the status of the crack, what is the location of the parameter. Okay, so here's an example that we can play. That would be great. It's a YouTube video. I don't know if we can. I think we just pass. No words is not possible. Might not be easy to do it. That's okay. That's okay. I think I can just explain what that was. So that was just sort of monitoring the move in the ground, because there are some settlements sometimes in the ground, and then they start moving, and they use acoustic emission to successfully monitor those, and there are other examples. So this is ultrasonic inspection. Ultrasonic is quite similar to acoustic emission. You have again the wave, mechanical wave, but this time what you do, you use a probe and you send a signal and you receive a signal. In the previous one, what you were doing, you were just hearing what's happening inside. Now you're actually intentionally sending a signal to see if there's a problem, then it can be reflected and then you detect it. It's similar to ultrasonic, that you go and doctors do the scanning of a broken bone in your body or something similar. That they do a CT scan. This is very similar to that we use for industrial application. So the wave that is reflected from, for example, a crack, so that we can know there's something wrong in our structure. So this is another way. So ultrasonic pulse velocity is quite similar. You send the pulse. You have so in the previous one we had just one sensor. It was acting as a pulse sender and receiver. In this one, we have two sensors. One is sending the signal, the other one is receiving it. Again, similarly, there are some ways that using time of travel and a few parameters. We can, for example, see what's the compressive strength of the material. Pulse velocity tests, for example, you put those sender or receiver in different locations in the structure, and from that you can understand, for example, whether concrete has uniform properties, whether it has any changes or there is a problem with the strength or not, whether the young model of elasticity and other parameters are constant and they have changed or haven't. Yeah. One, is it possible to play or? I think it's not here. Well, this one. So this was just showing what's going on, like with different, methods. We just use imagination of what I discussed in the session. So eddy current. Yeah, if you push some more buttons, okay. So different technique that is being used. So you have a conducting material, or you have induction, we call, and then this magnetic foil that comes to the material has to be conductive. And if you have any problem on the surface of the material, they're usually used for surface or near the surface damage. So then there is a change in the magnetic field that is detected by the sensor, and from the change in the magnetic field, you can say that there is something happening in the structure. So you see that eddy current produces magnetic field, and if that changes, then you can detect the abnormality. So there are different, examples of how it's being used. As I said, it's well suited for detecting surface cracks. But also, they can be used to make electrical conductivity and coating thickness measurement and a few other applications. All these techniques I'm discussing with you, they are in a wide area of research and developments that have been done, and there is still a lot of work going on. So not easy to explain in one slide what's one technique and what are the development. I'm just giving you a flavor of what they are and how they evolve. Right? So this is the infrared thermography. You have like a change of the color map. Hit color map change because of the defect, for example, that you have near the surface, and you use that mapping for detecting the structural health state. For example, here is the intentionally created defects in a concrete structure. It's a fiber reinforced structure. So concrete and fiber reinforced together. So they have got some defects that they have made artificially, and they use this thermography technique, and they are detectable because of the color, the difference in the hit color map. Well, and the last bit, which I'm going to then give the floor to Dr. Swarta to talk more about this self-sensing structure, is you actually design your structure to sense itself. For example, you have a concrete material, and you add some electrical conductive material or inks to sense itself. So what happens, then the structure is generating some data that you can sense. Like it can be the change in electrical resistance, or it can be change of the color. Then in this case, for example, we have a self-sensing cement coating, which is a conductive material that is damaged, then the electrical resistance of this layer is changing. And from the change variations, you can understand what's happening in the structure. Then,
Maybe you can fix.
oh, I think I'm almost done, but let's see. Is this okay? So we're changing. So yeah, well, one of the advantages of self-sensing structures is that they are multifunctional. You have a structure that is designed to carry the load, for example, but that also acts as a sensor. So you don't need all those previous, sometimes you don't need, sometimes you do. For example, you don't need the sensing element. It's the sensing element itself. Well, in some cases, you may need a data acquisition system. In some other cases, you may use just the naked eye to visually see it, which is going to be the case in what we are developing in small composites that are visually detectable. And usually they have got better durability, because one of the challenges I mentioned is the long-term performance of the system. because the sensors may get degraded during the life because of environmental changes and many parameters. And there are some issues as well, these changes may cause problems with the mechanical properties of the material and a few other things that also, get considered as a challenge. And here is an example of sensing concrete here, for example, that they have used cement matrix composite containing discontinuous, randomly oriented and well-described carbon fiber. Carbon fibers are conductive. And what happens if there's a crack? It cuts off the carbon fiber. And when it does that, you have less conductive material or higher resistance to electricity. And by measuring the change in electrical resistance, we connect that there's damage in the structure. Then you can calibrate that based on the structure level. I think this was, I think that's my last slide, and I hope I was not too quick. But yeah, well, if you have any discussion, any questions that you want to have, well, more than welcome.
We can have a discussion for the first speaker. And I will receive 3 questions. First part. Any of you want to ask question? Online participant, the question, you can type it on the chat room. Then you can direct the question to the student. Anyone from this? No? Not yet? Okay, if not yet, then probably I can raise a question.
Sure.
So, most of the monitoring systems that is the development is based on all purposes non-destructive testing, isn't it? Yes. And the newest one probably is this one by using a fiber. But is there any other material that can be used for monitoring also the fiber and the segregation?
Yes, there are. I mean, well, self-sensing materials is an emerging field that there are a lot of developments. One of the areas that they are doing is about change on electrical resistance, which I explained one example here. But there are different ways they are doing it, and there are different type of materials they're introducing. The application is not just concrete, but also many other applications. For example, they're using road monitoring, and they can use this conductive materials, also other type of materials such as magnetic materials, where they put the magnetic materials inside the manufacturing process, and then by tracking those magnetic property changes, they understand what's the behavior. So it's sort of, and also many other ways that they are doing it. Perhaps too many examples of them.
Let's see. And the one that you are developing at the moment is
our area that we are working, or I have two focused areas. One is the composite materials monitoring, fiber reinforced composite material monitoring, and the other is cementous concrete materials. So reinforced cementous materials, and then we are also doing different type of techniques that, one is the acoustic emission ultrasonics and magnetic sensors, the other area is mechanochromic materials. Mechanochromic materials are the materials that are developing novel layers that they are changing their color. So, when you are applying moisture, for example, then they change their color, and from the color change, we can say what the status of damage or strain level they are. So that's sort of as an early warning visual inspection.
Okay, any question from the participant?
carbon fibers. And carbon fiber is can be moved to the next level.
Sure.
It is randomly oriented. Okay, and this is also continuous. So
Yeah, it can be.
and this kind of thing can also act like a stress concentration inside.
Yes, or it can reinforce it as well, because carbon fibers are being for reinforcement purposes. So in most cases, they actually increase the strength of the material because they are considered as a reinforcement. But yes, you are right. In some other cases, if you are not designed, if you don't design properly, they can act as a defect and they can cause also problems. But mostly they are reinforcement materials.
So the key now is on how well
Yes,
each person
yes. And also what type of materials. It's not always carbon fiber. You may use like a different type of metallic conductive material as a powder, for example. Or many other examples. It's very much what you want to do, what type of material you want to measure, what mixture you have, and many parameters. Sometimes carbon fiber can cause galvanic behavior. Then it's not a good place to put because you will get corrosion or other parameters. So it's not always use of carbon fiber the best solution, but it depends on what you want and how you want to do.
Okay, any other question? Student? Participant that are attending online and offline? Then if there are no other questions, so we can continue the second session. Probably we have any questions regarding the topic of discussing the Professor online, and you can ask that after the second session. For the second session, thank you very much, Professor Mohammed. After the first presentation from Professor about the subtract concurrent system, it's a very interesting one. We'll continue with the second speaker, is Putu Swata PhD, the lecturer of Department of Mechanical Engineering at Surabaya. He already finished education from his degree from University of Bristol. Before that, he has doing a master degree in University of Technology Sweden and the bachelor degree on mechanical engineering University of Jakarta. And have a lot of his recent experience is mostly in the composite. And he also becoming the distinguished associate for continuing what he studied during his PhD on the Bristol. At the moment, we have quite a lot of papers to publish. I think that's what we about to Suwata. I would like to give the time and for Mr. Suwata to present his topic today. Time is yours.
Okay, thank you, Dr. Mubarak. We call it here, usually we call the elderly Pak, the elder. And to thank you to Retno from Physical Engineering. We welcome also Bu Doti, Dr. Doti, that teaches us universities. Also, you did a postdoc in Delft also. And also welcome for all the students and friends. So yeah, this is it's also related with what we call sensor, the smart sensor or adaptive structure. So a structure that could carry a load and also give an information about the state of damage that has already occurred on this material. So why do we call it high performance pseudo-ductile composite? So yeah, as we know that usually mostly in carbon fiber, that if they work alone, they fail in a brittle manner. They just snap without any sign of deformation or a visible sign of damage. So actually, this research was conducted by the Imperial College of London and with the University of Bristol. And I was one of the PhD students working on this project. And also Dr. Putri was also a postdoc, was also working in this project. So I think it's still continuing until this moment. There's still more room of improvement for this pseudo-ductile composite. So so why composite? So let's start why composite. So composite, they are strong. Besides they are strong, so they can carry quite a load, and they are also lightweight, so we can lift it quite easily. And they have as well as the like polymer composite and carbon fiber, they have quite a high resistance to corrosion and chemical attack. And also the other advantage is that they are flexible, so that we can shape them and reduce them into different complex shape, like a body of a car or wings of an airplane or part of a drone of a structure of a building. And also, so that's why we use the composite. So mainly it carries out from the automotive industries and also transportation, where they need a lightweight structure and also a strong structure. So this is kind of the application of composite material where we need a high strength, weight ratio, and also low density, also a high heat resistance. For example, a turbine blade that has been coated with some kind of ceramic, and also better fatigue properties, very corrosion resistant. So it's mainly used also in transportation, and this is NASA and also a bicycle, and also some part of a building also they're using a composite material. So yeah, for example, one of the most highly used composite material is carbon epoxy composite. So they are stiff, strong, and lightweight, so you can carry them like this body of a BMW i3 car. So two people can carry it, and also nice bicycle, carbon bicycle. But what is the drawback, disadvantage? So yeah, and the break is break easily. It's like that. So it's like a brittle and sudden failure. And also the type of damage, for example, if there's an impact on a body of an airplane, the damage could be located beneath the surface. Which cause difficulty to see or access. So due to that, so usually that there's an upper design. So we design a lot, some more structure, and also we are catastrophic and brittle failure. But so this is the aim of the program, of the Hyperduct program, is what if we can design composite material, fiber composite material, in this case a carbon fiber composite that can behave like a metal when there is a load acting on it. So is it possible if they can deform first and then there's a physical damage? So if there's a physical damage, it means there's an early sign of warning. So we can act, and then we can replace those parts and take a necessary step. So this is a aluminum bicycle. So maybe most of you has a aluminum bicycle. Okay, so this is the challenge of this program, Hyperduct program. So is to create and design and create a carbon fiber composite, for example, that could behave more like a metal. So in here, carbon fiber composite is what EY consists of the composite. It's more likely there's only a elastic material, and there's a damage, and then it drops at a quite low strength. But with aluminum, this aluminum, you have a linear elastic, and then you have this plastic plateau. This is what's the aim of this project was, and still. So There are three types of approach that we can use to create ductility that have been successfully demonstrated. So, for example, we can use this hybrid concept, and hybrid concept between high strain and low strain material, where we get a fragmentation and dispersion lamination, and we get this nicely elastic and plateau. And also, we can use this concept of angle climb, where when we put a load to fiber will rotate, and then there will be quite a nonlinear region also. Or we can use a discontinuous fiber embedded in cytomatic, so it will pull out slowly. So this is the three type that has been successfully demonstrated. Okay, so I would like to talk about first brief introduction about the fragmentation and hybrid lamination. So as you see in here, so we have this elastic behavior on both the high strain material and low strain material. So what if we could combine both of this material to have an elastic and plastic behavior? Yeah, it is possible. And then, but the key thing is the thickness ratio between the high strain and low strain material. So in this case, the high strain material is a glass fiber, and the low strain is a carbon fiber. But you can maybe pick another material which have quite an adequate strain ratio and also a stiffness ratio. So there's four cases here. For example, if the low strain material is thicker than the high strain material, so you have this catastrophic failure, and or you will have this low drop and then followed by catastrophic lamination. But here, these two cases is more preferable. So fragmentation, so you will have this elastic and plastic behavior, or fragmentation followed by dispersion lamination. You will have a more extended plastic region. So this type of gradual failure is much more favorable. So this is an example of an experiment and also an analytical method that Dr. Jalapan, Dr. Zusal and Professor Wisdom in our team developed. So this is a kind of a damage wood map. So based on this damage wood map, we can design our material based on the stiffness ratio or strain ratio between the high strain and low strain, and also the thickness ratio. So the ratio between the mechanical properties in this term as the stiffness and also the strain and also the thickness ratio. So yeah, preferably we would like to be in this area. And based on this damage wood map, they tested several types of carbon and glass layer. So you see this type of nicely linear and then followed by plastic region, and so also this other part of second linear part. And this is different type of carbon and different type of glass that you use because they have designed it to be in this region. So you see nice plastic and layer and plastic. But the other advantage is, as Dr. Putri has mentioned before. So here, with increasing of the strain, you'll see when there's a damage occur, you'll see a change of color. So they can also carry load, and then when there's a damage, you see a change of color, and then this change of color is related to certain number of strain. So the number of strain. So this is quite nicely. Okay, then next slide. So before it was a UD, now it's a QI, quasi-isotropic hybrid. So the UD is on the fiber is only running in one direction, but for quasi-isotropic you have a fiber in other direction. For example, in 0, 60, minus 60, or 45, minus 45, and 90. So also they also successfully developed a damage wood map for this QI hybrid composites, and to have more dispersed fragmentation and lamination. So next, please. So here's Dr. Putri and Dr. Jalapan and Professor Wisdom has successfully demonstrated that it is possible to have also a pseudodactyl response in QI composite with this nice linear and also plastic region in both cases. But they also added the load, not only the load in zero direction, but they put the load in every fiber direction, 45, 60, and 90. And based on this experiment, a nicely pseudo-data response has been demonstrated. And also there's a change of appearance. So based on this change of appearance, you can see the state of damage or the type of strain endured by this material. So what if we added a whole of stress concentration? Because sometimes in in a airplane part or a car part, we need to put these two parts together. So sometimes there's a needed for a hole, and then we put a bolt there. So here we can see that increasing damage, low level, increasing strain level, we can see visible damage on this knots. With different type of knots, you can see increasing type of damage, and also increasing damage initiation for the open hole and sub knots. So this is knot one, and this is open hole and sub knots. But the damage here, the other advantage is the damage initiation increases due to this hybrid concept. So yeah, and the other application is the high strain rate for this hybrid composite with different high strain rate. There's also similar pseudo-ductile behavior with a change of appearance. So this is quite interesting. So yeah, I think the high strain. So it means that even though the load is quite fast with this increasing high strain, you still have this pseudo-ductile behavior. So it's quite beneficial for other type of application. So if we move to the fatigue loading of UD hybrids, again, there's a quite slow damage growth and a slow stiffness reduction at 90% of the 3-point strain. So the deep-point strain is where the fragmentation on those stress strain curve has appeared. So you see, it's quite slow at 90%. So when we did it, we have to wait for we have to leave the specimen for like 24 hours in the lab until it completely delaminates because it was quite slow. This is a typical stiffness reduction and normalized delamination growth. But at 80% of the knee point strain, there's no visible damage and there's no stiffness reduction. So this is quite good for fatigue application. And we have also successfully demonstrated that for the QI hybrid, when there's a fatigue loading, for the anodes, the damage growth is quite slow. Also the stiffness reduction is quite slow. Also for the nuts one, it is quite slow also, and there's a visible damage growing near the hole. So yeah, it's quite good also. And another thing about carbon fiber composite is that they are quite prone to sudden and brittle failure during compression. That's the problem. So we try to tackle it by using this hybrid concept. And stacking glass, carbon and glass, and we conducted a direct compression performance on this kind of material. So this is thin M55 carbon epoxy. It has around 280 gigapascal and standard S-class material. The key thing is the ratio between the stiffness and the strain. Also, we change the number of layers to see the behavior if we use different layers of carbon. And this is the type of direct compression loading picture that we use in Bristol. So we'll have a direct compression here, and the load will be transferred through the end tap through here. So then this next. And then we successfully demonstrated that there's quite a nice also linear and non-linear behavior for different carbon layer thickness. And also the interesting part is also we can see this type of change of appearance during the compressive loading, and there's a visible change of slope, visible change of stiffness around 1.5%. And yeah, this is at least the first time that we have demonstrated this behavior. So what if we move to another type of loading, for example, grinding? So if we sandwich the carbon within a high strain glass, and then we put a forward point load. In this case, this is the same type of carbon. We will see also quite a change of slope. So this change of slope is related with the appearance of fragmentation and amplified. So this is a scanning electron microscopic picture. You see here is a carbonate fracture. So due to the fracture, it changes the stiffness, and then when you see it from the top, there's also a change of color of appearance. So this is quite nice also. What about the other type of loading? So Dr. Putu also conducted this compact tension, and you see from this compact tension here, the red curve here shows a pseudoductile behavior, and this is the carbon, and here's the glass. So you can see it's a pseudoductile behavior, it's a combination of both material. And Dr. Putu also conducted an acoustic emission examination in this material. Is quite a there's quite a signal. This signal is as a sign of there's a damage occurrence on this material. So this is the concept that we use for this nice compact tension. So there's a hole here, and we added I think you added some layers here for the compact tension.
Yes.
Okay, so this is a quite interesting application, and also you see a physical damage also in the material. And also if you use, this is a bypass rate, so this is more aligned related to the real application. So here's the hybrid material or composite material, and it is bolted, so there's a joint, and when we add and we put the load, there's quite a physical damage here. So this is a different set of damage between QI carbon to QI glass, and then the hybrid. So you see the hybrid, there's also a change of color and a nicely quite nonlinear behavior. And this nonlinear behavior, it fails at a displacement much higher than the carbon itself. There's a possibility also to see the damage on the surface because of the change of the color. And there's the thing, we still need to see, to inspect the damage in the middle for the end composite, even though we can see it through the surface.
Yeah, to connect those differences.
Yeah, because it impact also the damage in the surface, and beneath the surface is quite different. So we need to characterize and all through. Okay, please. And actually this is the highlight of this UV hybrid composite, that we can use it as a sensor. So for example, we have a matter, for example, if this is an aluminum or stainless steel, and we can add this hybrid composite on top of it by using some kind of addition, and then when we pull this or we put some kind of strains, it will change color, and then this change of color to be related to the strain level that it has endured. And this is one type of example that we use in a handlebar of a bicycle. So we have designed this so that the strain, the damage sensing is activated at quite high displacement. Due to the confinement of a glass, so when the carbon breaks, the glass confines it, so it won't break easily. So this is quite nice. The sense of activation, when you activate here, you can see the change of color in the handlebar. Okay, next slide. So another type of concept that we can use to introduce pseudoductility is angle ply. So this angle ply, we use like a thin ply carbon with a thickness of 0.03. So yeah, what happened is that when we put the load here, the fiber rotates and we have this nonlinearity. So it is possible for the fiber to rotate because the matrix is more ductile compared to the stiff carbon fiber. So it was adopted by our colleague, Dr. Fuller, Jonathan Fuller. And what we see here is there's a nagging visible deformation. So it's not that it's different concept than the hybrid composite, the UD ply, where we can see the change of color. Here we can see the change of shape, a nagging. This is quite like a method. So this is quite interesting. A nagging. This can be designed also. So another concept is that this continuous composite or short composite. But before it was a continuous composite, so now we move to a discontinuous composite. So a short fiber. So maybe before we go. So yeah, this short composite, the length of the fiber is quite short, so around 3 or 6, 12 millimeter. So the key is to have this short fiber aligned inside the polymer composite, so it could carry the load quite easily. And also the advantage by using this continuous composite is that we can make a complex part more easily compared with the continuous composite. So we can make it stiffer and we can use less material, but the key is here, the alignment. So we need to maintain high alignment. So the damage mechanism is like a slit between the carbon, the fiber and the resin. So yeah, Dr. Giselle, who is my second supervisor, he has successfully demonstrated the nonlinear behavior for this discontinuous carbon fiber. So also based on this discontinuous composite, can we go next? We can see in Bristol they developed this technology called high performance discontinuous fiber. So this kind of discontinuous fiber were aligned by using this concept. It was put inside the water and then there's an injection. It's injected into a plate. So when it hits the plate, so it aligns itself. So this is the type of technology that they have been using to reduce the high performance discontinuous carbon fiber. So this is the optical microscopy in this cross section. You see that it's quite aligned. And based on this, they also manufacture and develop also a thin ply hybrid carbon. So if you go next. Also, yes, another. They have demonstrated that by using a different type of design, we can get a different type of pseudoductile response. So the optimal one is, two of the optimal one is the intermediate and dispersed. So we have linear and non-linear type. So this is a mix between a carbon and also a glass. So by having the carbon dispersed within the glass, you can delay the fracture and damage propagation. So this is quite nice for discontinuous. So it means that by using this continuous type, you can also have a pseudoductile response. So next. So yeah, and they have also demonstrated that by using different carbon fiber fold fraction, we can also have a different type of pseudoductile response and a change of appearance of the color. So it can be used also as a sensor for this discontinuous fiber. So this is kind of the concept. So this is a continuous glass and this is a discontinuous carbon fiber. So it's nicely demonstrated. It can be used as a sensor and a load carrier. So yeah, the conclusion is the benefit of this pseudoductile concept is that we can use this to carry load and also we can use this as a sensor which could give an information of the states of damage and the level of strain that it has been endured. And also the potential to be able to express the better proportion of the favorite ultimate strain. So yeah, by using this hybrid concept, we managed to push the failure strain of the carbon much more higher than if the carbon works alone. And also, if there's a hole in this hybrid composite, we were able to manage to redistribute the load. So when the load is distributed, so it won't fail easily. And it means that we have greater energy absorption and higher toughness. Okay. And here's the conclusion for the hybrid composite. It also has a good performance in funding and also has strain rate application. And also we successfully demonstrated a non-linearity in compression, which is quite beneficial. And yes, the change of color. And also it has a good notch in sensitivity, so even if you drill a hole, it won't fail that easily. So next. So the other approaches has been successfully demonstrated to give a pseudoductile response for the angle flight and for the discontinuous carbon and glass fiber. That the key is that we need to redistribute the load and to make this failure propagates slowly. That's the key, and it is dictated by also the thickness of the carbon layer, the thickness of the glass layer, and also the stiffness ratio, strain ratio. Yeah, also the fracture toughness. Fracture toughness comes in play from the resin properties. Okay, I think. Yeah, this is the references. If you would like to read, I think we have also many references and many. I think is coming in this. Many publications will come. So yeah, thank you very much. If you can, if you would like to talk or discuss, and then maybe there will be some collaboration which we can establish with Dr. Putuhi. Great. Thank you very much.
Thank you very much for Dr. Pascasarjana for the presentation. Any question from the audience that present in the class? From the audience, is there any question? Was there? Okay. If not, then I will just raise some of the questions. The first one is it's very interesting to see that the composite that usually we have brittle not can be tuned to behind the fire. And the question that I have is there any fiber configuration that is required to create the ductile composite, as you mentioned before? Is there any fiber configuration that you have to tune to create the ductile composite in this case?
Okay, so I answer or would you like to answer? Okay.
So I think you
Oh, yeah. Okay. One of the things that is important, for example, let's start for the UDT fly hybrid composite. Or for example, if you see the continuous hybrid composite is the thickness ratio. So we need to have as thin as possible of this low strain material. And yeah, this glass is 0.15, so this carbon is 0.03 millimeter. So yeah, the thickness ratio needs to be tuned, and also the stiffness ratio between the carbon and the glass needs to be tuned. So a stiffness and strain ratio. So if we have a quite thin, carbon here, and when it fractures, it won't delaminate quickly. So it will delaminate slowly because of the low stress here. And also the other key point is the fracture toughness. So this fracture toughness comes from the Yes, to capture from the epoxy material. So basically, all of this is the epoxy material. But if we talking about the fibers, the stiffness ratio or the strain ratio between the high strain and low strain, and also the thickness ratio, it needs to be tuned based on this damage what map to have this pseudo behavior. So yeah, maybe you would like to add.
Perhaps the damage mode map you can show.
Oh, yeah.
That also helps.
Yeah, the next line. No, this is the damage model. So the glass of carbon proportion is related to the thickness ratio between the carbon and the glass. If you see the thickness ratio of carbon becomes larger, so we'll have this failure, catastrophic failure. Or if the carbon layer thickness is quite high and carbon and glass proportion is quite high, also will have a fracture and quite quick lamination. So here's the area that we are more interested in to get this pseudo behavior. It's a quite low or beneath 0.3 the carbon glass proportion and quite thin carbon layer. So around 0.03 is quite good now. So here's the proportion and also the carbon layer thickness. Here's the number of strain. So here's quite high strain. So here's the area that we are more interested in to get this pseudo behavior. Yeah.
Okay, thank you very much. Any questions?
Thank you, Pak Hedu. My question is, could you please explain what kind of carbon materials that we use? Any carbon has so many allotropes like graphene, amorphous carbon, or others. So, what kind of carbon?
Okay. I think this is a Well, we use MP5 and EC25. High strength and high modulus carbon. I think it's kind of graphene carbon. It's a continuous carbon fiber. So it's fiber. Prepreg. It's a prepreg. It's like a sheet, number sheet. So this is like a sheet. So we just add it on top of each other and then we cure it inside the autoclave with a curing temperature 125. But I think at least I think it's kind of a graphite. It's called the high modulus.
Yeah, but there are different versions of materials you can use. There are a variety of prepregs, carbon prepregs with manufactured in different processes. They have got different young modulus and strength to failure process, values, and they all can be designed to behave similar.
Okay, understood. Thank you.
Thank you, Dennis.
Other question?
Just the student. Yeah.
During the thought process.
Thank you. So I think this is very interesting because you try to delay the fraction in such a way so that you can be more straight in the materials. I think the behavior is also quite similar when we work in using metallic materials. We change the orientation of the fiber, but we never can also change the texture of the materials. Because this is also depending on the direction that you test yourself. In this way, what is quite interesting for me is that how can you maintain the contact between the low strain materials and the high strain materials? Because in composite, it is very crucial to have a very nice bond between the low strain and the high strain.
Okay, yeah, thank you. That's a good question. It's quite crucial, actually. And because since we use a prepreg, we bought it from Torre and also SK Chemical. So it's an epoxy base that we use here. So the epoxy base we cure it with the temperatures 125 degrees, and after curing we examine it under optical microscopy. And at the moment before we put this tensile loading, there's no like a phase variation after curing, but after we put this tensile loading, for example, in this case, so because the carbon is quite thin, and then it's able to fracture and laminate slowly because of the thin carbon ply. So this level of stress is hybrid composition is not quite as high as, for example, for this thick laminate. And also, I think what matters is also the fracture toughness. So because this is epoxy, it's quite compatible. So the fracture toughness is quite high. So it's still able to carry the load with this nice fragmentation. I think also maybe the fracture toughness also comes into play because this is the same type of resin epoxy. So it seems that the fracture toughness is quite strong and good. But of course, with different type of resin and different type of thickness, maybe it will be different. But we need to maintain, I think, the fracture toughness. Okay, thank you very much. Maybe this other student.
Okay, from the student, is there any question? Need to practice your English.
Yeah, come. You need to go to see the world.
Anybody want to raise their hand?
Please.
Yes,
Yeah.
the study will have another question.
So what about the shearing process?
It's
Do you have any shearing process?
Cheer.
During the test?
Okay. I think this year comes in play for the angle ply. And we can see the angle ply. Play the next slide, angle ply. Next slide, angle ply. You can go next. You go next. Okay, this is so shear modulus and shear stress comes in play here. So when there's a rotation of this fiber, there's a shear stress between the fiber and this resin here. And because the fiber is deeper than the resin material, it's able to rotate, and because of the shear stress here, so it kind of damages the matrix, so the fiber could rotate. So here also angle ply could also be used to measure shear modulus. Yeah. So we also use this concept to measure shear modulus. So shear also plays a role, and also because of the shear stress, it could also cause delamination, add delamination if the carbon is quite thick. So because the carbon is quite thin, so it was able to deform without any substantial delamination. So this is quite nice. So yes, here does it plays also in QI as shear stress.
Yeah, well,
If you want.
no, I think in mainly angle plies, you have the shear behavior. Of course, shear loading is also depends on how you load the structures. You know, if you do tensile, you don't get the shear in unidirectional ones. So of course, you get some sort of shear in isotropic as well. Or if you're doing bending, for example, which we showed some of the results there, then you have the shear stress as well, but it depends on which one is dominant. So it's about the competition between the failures. And in some cases, the competition, like here, the competition is with the rotation, then it fails using this type of failure. In others, it's more fiber-dominated failure. So yeah, it depends on usually the stress and distribution, and also of the competition between the different type of failures. Thank you for the question, but these are very relevant and important questions. Spot on.
Thank you. For the student, you can ask practice. This is your chance.
Okay, one question from.
Actually, I want to ask you mentioned earlier about the whole stage of structural monitoring. There are 5 stages, and if I guess correctly, it will connect them to predictive maintenance and etc. So in one stage, you have to do the predictive and the conditional and preventive. So if you have the level states,
So the levels of structural health monitoring, level 0 to level 4.
And was setting, I mean, like, for its level, what should we do with the data for the maintenance?
Yeah, well, I mean, it's very much application oriented and what you need from the design. To give you some examples, for example, you have a chair and all you need to do is to see whether it works or not. And if you don't like it, you're just gonna replace it. But there are some complicated and expensive structures that they may fail locally. Like, for example, imagine a bridge. A part of the bridge is going to fail, and you need to know what type of failure you have in order to make the right maintenance or the repair for it. Like you can repair it or replace it. So basically what I'm trying to say, the choice of what type of level and what type of structural health monitoring complication you should put in depends on what you need from this monitoring system. Is it just to give you an early warning that you need to replace something? Or is it to give you more information? Okay, there is something, what is the effect of that on the overall performance of the structure? So if that's the case, then you need to get more data and understand, okay, we have a size, for example, 2 millimeter or whatever. This 2 millimeter defect is causing 10% reduction in the strength of the material. It means that in the longer run, you're going to have failure of fatigue happen like 10,000 cycles earlier. So we need to do something earlier than what we have designed for. So it's more the application and how you want to use, that system for your purpose. Thank you.
Okay. Anybody want to ask another question? Is there any question from the online? Nothing. Steve, if nobody asks another question, we can end the session for the second speaker, Mr. Swata. We will take for applause for Mr. Swata. So, when you are finished listening to the chief presenter, Professor Muhammad Fadhari and Mr. Swata, and I would like to give you a big thanks for providing us the possibility to learn from your expertise this morning. And then another thanks, of course, from me, especially because of your time that you're providing for us. And I will return the session to the MC before we are closing up the webinars. Thank you very much.
Right, so thank you for the session, the lecture session for Mr. Swata and Muhammad. Before we close this session, this program, I would like to invite everyone to come and take a photo together as a recommendation. So please, very nice to stage.
There's not space for everyone. Perhaps we can go down.
Yeah. Oh yeah. For big guys.
Pikir Pak Fahmi.
Ini. Segmen aja.
Kayaknya lebih merapat dari sini.
You have a space here as well if you want to.
Satu, mungkin yang lepas masker. Satu, dua.
Thank you.
This is all for today's session. Thank you so much for coming here. You can see each other in another session with the webinar. Thank you so much for coming and Assalamualaikum warahmatullahi wabarakatuh.
Tidak saya kira video tinggal apa
Cookies.
Ikan con datang ke masyarakat kalau masuk ke terima kasih Pak.